thank you everybody for being here. So this is part of a project I started a few years ago with Edgar, now Arturo Arellano, who's a PhD student in McGill, is also working on this, and quite recently I have also been talking with Mariana about some results, no? And I want to tell you a particular part of this project. But before that, I will explain the big picture, you know, what is this about and why we believe this may be interesting, no? So a little bit of motivation. Okay.
No, just maybe we have to go for screen.
You think it's going to disappear eventually with time? Well, let's see. So we're looking at these type of problems that appears in race theory and in storage, and they have a very particular equation that caught our attention. No? So I will explain you in a moment how they come about. But you see, it's a very nonlinear problem. So V is the unknown function, no? And then you have a differential operator applied to V. Think that L could be the Laplacian, for instance. And then you have 1 minus the first derivative of V, no, in the direction x1, and then something similar in the direction x2. And that combination, which is very nonlinear, you take the maximum of those three numbers has to be equal to 0. No? And this is very curious because it's going to be connected with a problem that we have studied a lot in elliptic PDEs, which is called the obstacle problem. So this is some sort of obstacle problem for the first derivative. So let me explain why we believe this is interesting, no? What? Okay.
When you move the finger, because you have your Zoom screen at front, no?
Yeah. Okay. That's it. Okay. So how this comment, where this problem comes from, no? So Rick's theory think that X, no, is modeling the amount of money that has an insurance. The X, smaller S, is the initial amount of money. And at every time, the people that is in the insurance is paying a fixed amount, P. So all this time is where you are doing your payments to the insurance, and then accidents may happen, no? And then the insurance loses money, and this goes on until the time where the insurance goes to ruin, no? Where this quantity becomes negative and you're broke, no? So what's the problem? That you want to offer your shareholders, no, a way to give them back their money in an optimal way, no. So you want to give them as much as money as possible up to the time of ruin, no. If you give them all the money at the beginning, that is going to be a bad strategy because the company is going to go bankrupt very quickly, and then you need to do a balance, no. So that was one of the first instances, I would say, of an optimal control problem. It was studied by Lombard, Kramer, and Definetti, no? So how do differential equations come about in this setting? You think about the value function. So the value function encodes what would be the optimal strategy when you start from X, no? So actually, V of X is what would be the best that you can do in expected value, because there is a random component in this problem. So this will be the best that you can do, no, given one of these strategies, no? So L is the amount of money that you pay, and I'm assuming in this problem that I don't have only one insurance, but I have multiple insurance. So you may think that there are two, no? So now my X, this process is multidimensional, no? And ruin happens whenever I escape the positive quadrant. Okay? So I'm paying this amount of money to people, and then we notice that you can compute the V by some sort of infinitesimal recurrence relation, no? If you know how is V, an instance after, at every possible position, then you can compute V at the present. And this is called a dynamic programming principle, no? So the idea is, you have V, this is a process that is driving the dynamics, and then L is what you're paying to your shareholders, no? And then V at this position is an instant, you take a peek into the future, no? And this expected value is what you will get, no? From what will be your optimal, no? Your optimal value, no? And this is what you have paid with that strategy in particular. Among all that possibilities that you have for this L, for this vector L, you take the supreme of that, no? So this is kind of an infinitesimal recurrence relation. And actually, the next thing that we do is just subtract V of x on both sides, divide by the dt, and send dt to 0. And what you recover is a partial differential equations, which is it has a non-linear structure, no? Here encoded by the supremo, no? This is called Hamilton-Jacobi-Bellman. And here is where appears this. Usually it's a non-local, but if the process is being driven, let's say, by our favorite stochastic process, like the Brownian motion, this will be the Laplacian, no? And in general, it's called the infinitesimal generator of your process, no? So you have this equation here, and then we can unpack a little bit what it says, no? Notice that we have the product of these two vectors, L's. The L's are always non-negative, no? And if this factor, no, would be positive, no, at least for one of the terms, then you get that this quantity will be infinity, no? And you want to avoid that, no? So actually what you need to ask is that all these coefficients here in front are non-positive, no? So that means that you need that all these components of the gradient are bigger or equal than 1, no? And when that happens, when all these coefficients are negative, in order to maximize this, you take L equal to 0, okay? So you get this very strange system because now you have a bunch of restrictions on the gradient and a PDE, no? The bad news is that this problem is overdetermined, no? There are too many equations. So what we do is some sort of relaxation, and instead of asking for this, I'm going to ask the smallest super solution of this problem. So what is going to happen is instead of asking for all these inequalities, I'm going to ask, well, still there is my constraint. I'm going to ask this operator to be bigger or equal than 0. And in the case that my minimum is strictly larger than 1, I take I need to satisfy the equation exactly, no? So this is very, very much related with a very similar problem that we know, no? Which is finding the least super solution, no? U for a function that is above a given of phi, no? So the restrictions are U bigger or equal than phi, no? U is superharmonic, no? And whenever U is above the obstacle, no? Then you have that U must be harmonic, no? So now this is something very similar, but for some conditions on the gradient. Okay? So the first thing we saw this problem and we said, well, probably we should try to do something easier first. This is too complicated because it has several ingredients that make things quite technical. The first one is the non-locality of the operators that appear here. No, if you have in this illustration that I give you in finance, usually this process has jumps, and the type of operators that appear are integral differential. No? So I'm going to substitute this by the easiest operator that I can work with, just the Laplacian. And this condition is still more challenging. Yeah. So here I'm going to do an abrupt idealization, say that this is just the length of the gradient. So this is how we come up with this type of equation. Notice here I also make this operator homogeneous. I don't care about by scaling. Actually, this is if you can do the analysis for this type of equation, you can do it also for non-homogeneous terms here in the Laplacian. So let's just focus on this one. And then we see this equation and we say, well, we need to justify somehow that this is a problem that has some motivation, no? And here is a problem that I can find quite interesting, no? So you have it's a zero-sum game. You have two players that have totally different objectives, no? Let's call them Rick and Morty. So one of them wants to explore the domain omega. So he wants to stay in omega as long as possible. Both of them are driving some spaceship, and Morty wants to get out of omega as fast as possible. So what are the choices that they take at every moment? Rick decides if he drives the spaceship or not. And if he lets Morty drive, Morty is going to drive at maximum speed in some given direction, no? So the value function, in this case, is going to be the time, the expected time for you to escape the region omega if you start at X and follow optimal strategies, no? And if you do the same analysis as before, no, you are going to discover that the value function solves the following Hamilton-Jacobi equation, no? So it's the Laplace, or perhaps depending on your notion of the Brownian motion, you will put here a 1/2, no? So the Laplacian minus the Laplacian minus 1, and then you compare with the length of the gradient minus 1. The minimum of those two numbers has to be equal to 0. And again, this is an obstacle type problem, no? So in this case, instead of having something like this, no? You say, well, here I always ask that the gradient of u is bigger or equal than 1. Yeah. I always ask that my function is super harmonic, or no, not super harmonic, but in this case we are equal than 1, no? And it is going to solve the Poisson equation exactly in the region where the length of the gradient is strictly larger than 1. Okay. So let's see what have we done about this type of problems. So first, you may notice that it belongs to a particular class of degenerate equation that I have been studying recently. So let me write again the equation here so we don't forget. So this is the minimum, no, of minus the Laplacian, comma, length of gradient minus 1 equals 0. And this equation says the following, no? You are going to satisfy an elliptic equation if your gradient is larger than 1. Otherwise, well, your gradient is smaller or equal than 1, no? But this equation says a lot more, no? But here is the key point, no? So you are elliptic, you are in an elliptic regime if the gradient is large. Huh? Well, minus 1 is the no, this was correct. Okay, yeah, minus 1. This is the one I may be dropping along the presentation. No, I mean for the model you will put here a minus 1. Yeah. Okay. So look at just this equation. No, so this equation says you are on a uniform elliptic regime if your gradient is large. The alternative is that you are Lipschitz. And this is very nice, no? Because in the alternative you already have regularity for free, no? So the question and the very interesting contribution of Wimber and Silvestri is that they can say what happens kind of in the intermediate region, no? Whenever you are in a point that is in between, no? So you still recover Holder estimates, no? Another work that is quite related was done by Evans and also was studied by Schrieg and Sonner in terms of singular optimal control. And it has to do with the following equation, which looks very, very similar to what we have over there. So let me write it here bigger. So now we have, instead of a minimum, we have a maximum. And again, minus the Laplacian, length of the gradient minus 1. No? And if we unpack this equation, it says 3 things, no? So my function u is subharmonic. The length of my gradient is always less or equal than 1. And whenever the length of the gradient is strictly less than 1, I'm harmonic. Actually, this equation is much better than the previous one, because in this equation you get for free that the solutions are Lipschitz. Yeah, you already have that the length of the gradient has always to be bounded. So the contribution of Evans was actually more robust in the sense that solutions of this equation are C11. Okay, and actually it was later on proved by Bresis that and Siboni that actually this equation is equivalent to an obstacle problem, the classical obstacle problem with the solution of the Conal equation as the obstacle. Okay, so what we did with Héctor was to show that solution of these equations are not only Holder continuous, as we knew from Inver and Silvestre, but they are actually Lipschitz, no? And this is an optimal estimate. We can find solutions that are just Lipschitz. There is not more regularity on the gradient. And more interesting for us is that, yeah, the gradient of U may be discontinuous, but the length of the gradient of U is a continuous function. And you may understand this some sort of pre-boundary condition, no? So in your Icona region, the length of the gradient of U, so this is called, by the way, when you said length of gradient of U equals 1, that is called Icona equation, no? And in that region, okay, the length of the gradient is equal to 1, okay, almost everywhere, yeah? But what happens is that when you approach the free boundary, no, the interface between these two possibilities, the gradient of your harmonic function in that case is going to have a limit. The length of the gradient is going to go to 1. Okay, it's kind of the free boundary condition, I would say. So what we did recently was to understand this problem from the perspective of the second player. So the first player already declares its region, no? This is the region where I'm going to drive with a Brownian motion, and in the other region, I let you do whatever you want. And we want to understand this problem, okay? This, so you may understand here in this setting also, we have our region omega, and to the left, I have the region where Morty drives, and to the right, the region where Ricky drives, no? And it may be the case that my optimal strategy starting here is to go to the Brownian region, because you see, here I'm going to be very, very close to the boundary, no? And with a high probability, I'm going to escape soon, no? And then it may be the case that my Brownian motion takes me all the way to here, I get outside, and then Morty takes back the wheel and exits at this point, no? And something that you can appreciate is that in this problem, we know exactly what are the equations in the Icona and Brownian region. So you have length of the gradient of U equal to 1, and Laplacian equal to 1 on the right. And the question is, well, this doesn't determine a unique solution. You need to say something about what happens at the interface to have a well-posed problem. So this is what we're trying to do, no? And the first observation, how do we know that we have a chance to say something like this? Well, we start looking at the discrete problem, no? And this is what we are studying with Arturo, no? And we may think that in our discretization, the points are either Brownian to the right or Icona to the left. Okay, and each one of those points is going to have a discrete dynamic programming principle, no? So U of X is once again the value function, no? Now instead of moving with a Brownian motion, I just have a random walk on the right, and on the left, the player, the controller, decides where to move, no? And then you get these equations, no? So this is what happens on the left, no? In your next step, you spend 1 unit of time, and you look at the point that gets you closer to the boundary, no? If you're in the random walk region, you pay 1 for moving, and then you just have to average wherever you're going to end up in. And then you have a boundary condition, no? You are 0 if you're already outside of the domain, no? So this suggests that the actual condition on the interface may be irrelevant. So there is kind of no interface condition. So we need to make sense of this statement. And this is part of our contribution, no? So the first thing, so this is what I will try to convince you today. The first thing is that we propose some transmission conditions at the interface and show that all of them are equivalent, okay? Then we show that there is a comparison principle, and this is going to be important to establish the well-posedness of the problem, no? So there are solutions, and these solutions are unique. And now that we see comparison principle, for those of you that are a little bit familiar with the viscosity solution, you see that this is going to be a hard problem because the Hamiltonian that we're dealing with here is not only discontinuous, no, it's not only that has discontinuous coefficient from the left to the right, but it's also that it changes completely the nature of the equation. Okay, so let me give you a quick overview to the classical viscosity solution theory, no? So the classic, the viscosity solutions are the main thing behind the viscosity solutions is the comparison principle. And here, the comparison principle is something that we learn in calculus 1. It's the first and second derivative test, no? If you have two functions, U and V, that touch such that their graph touch each other at a given point, you know two things. The first derivative test tells you that their gradients are the same, so their affine approximations are the same. And the second derivative test tells you that their Hessians are ordered. In which sense? Well, the quadratic forms that they define are ordered, no? So let me be a little bit more specific, and here I'm about to define what are elliptic operators, no? So elliptic operators appear when you're studying a second order equation of this type, no? And I'm going to assume an ordering in the set of symmetric matrices, which is the ordering of their quadratic forms, no? So to matrices are ordered if and only if their quadratic forms as functions are ordered, okay? And I'm going to say that the operator F here is elliptic if it's monotone in the Hessian, okay? And notice here that the monotonicity is equals in the opposite direction. No? If M1 is less than M2, then F evaluated than M1 is bigger or equal than F evaluated than M2. So here, for example, what I call elliptic would be minus the Laplacian. Okay, so this is the notation of Lyon, Zuccarelli, and so on. No? This is also a line here because different books. Different people use a different notation, but this is the people I want to sell this result. No? So I choose my uncle line, no? And why is this important? No? Why this monotonicity on F is actually relevant? Well, first of all, it appears in many problems, many motivations. As you can see, well, the Laplacian is an operator that appears all the time. But it tells you the following, that you can extend somehow the second derivative test to these nonlinear problems. Okay? So what I mean is the following, no? If you have, as before, no? If you have here U and V, and they touch each other, so you have that VU equals to dV at the contact point. So let me call this X naught, no? And moreover, the Hessians are ordered, no? And if F is monotone, then the operators, no? Evaluated that particular point are going to be ordered, no? F, whatever, no? The same thing, but for the okay? So this allows you to extend the notion of what is a solution of an inequality like this using functions that not necessarily have second derivative, not even first derivative. So the idea is that you take a test function, a function that has two derivatives in a neighborhood of a point X naught, where phi is touching U from below. In this picture, V will be the field. And then you know that if this were a classical solution, if you can evaluate this and you want to say that this is bigger or equal than 0, then the operator evaluated at your test function should also be bigger or equal than 0. So you just keep that part and say, well, my new definition of weak solutions is just to ask if this inequality always holds. Okay? And this is quite nice because it's a very weak notion of solution that have a lot of nice properties. And in particular, has this stability property that allow you to construct solutions in a particular way. No? So stability here means that if you have a sequence of super solutions, no, super solutions come with this inequality, no, bigger or equal than 0. And I forgot to say that there is also a notion of sub-solutions. We come with the opposite inequality here, and here you need to touch from above, and here you need to check the opposite inequality, and solutions are those that satisfy both notions simultaneously, no? So what about the stability is that now, instead of having to ask that your sequence of super solutions converge in the norm C2 to a function U, in order to have that U inherit the inequality, the equation, you only need to ask local uniform convergence. Okay? So this is it gives you a quite flexible notion of solutions. For instance, if you want to show that solution exists in this setting, something that you can do is consider the whole family of super solutions of your given equation with some boundary conditions and take the lower envelope of that. And that's what is called the Perron's method. And the fact that you can do that actually relies on the stability. Okay? Something that is going to happen in our transmission problem is that we are mixing two types of equations. No? I'm doing good time. How much time we have?
20 minutes.
20 minutes? Okay. So you're mixing two types of equations. And this was already observed before in the literature, and this is called the general boundary conditions. So general boundary conditions appear, for example, if you want to solve, let's say, an elliptic equation in the interior of your domain, and then you have some sort of general Neumann condition on the boundary. Okay? And in this case, notice that to define sub and super solutions, including these two operators, you have to do something funny at the interface, no? So again, the idea is that phi, you have a test function that touches you from above. So you're testing here for sub-solutions. Then, if the point falls in the interior of omega, well, you need to check that this is less or equal than 0. But if it falls in the boundary of omega, you may ask if this is less or equal than 0, or if f, the operator that looks in the interior, is less or equal than 0. Okay? So it's either one or the other. It's very weak. And for super solution, it's something similar but with the max, no? Which means that either this is bigger than 0 or this one is bigger than 0. And this is convenient for the stability, no? Because when you have this proof of stability, when you are having a test function for your limiting function u over here, you're going to have that test function is going to touch each one of those functions in the sequence at a point that could be either in the interior or it could be at the boundary. No, so you need to relax. No, you cannot always ask, for example, that if by bad luck, no, my test function touches you at the boundary, but touches each one of those at the interior, you are going to lose information. No, so what you are doing is actually kind of relaxing, no, the notion of solution. No, so this gives us an idea of what we're going to do in the transmission problem. So what we do actually is to set up the transmission, the weakest possible transmission condition that gives me stability for this problem. And the bad news about this is that we don't know if we're going to have uniqueness for this problem. There are many things that could satisfy these equations, no? So what is the weakest definition, well, you still have a iconal equation on the left, or on the iconal region, the Laplace equation on the right, on the Brownian region, and on the interface you have to satisfy one or the other. Your test function touches you there, either your gradient is going to be this is sub-solution, so you're touching from above, either your gradient is going to be less than 1, or you're going to bend downwards. Okay, your Laplacian is positive, no? For super solution, well, you have something similar on the other side. There is a strong formulation of this problem, and at the beginning they don't seem to be equivalent. So let me just go to the point. Let me spoil you the end of the story, and the strong formulation is just to say that the length of the gradient, I need to satisfy the iconal equation, not only on the iconal region, but all the way up to the boundary. And when I say this, I say that I satisfy the iconal equation in the viscosity sense. No, if I get to touch at the interface, I only need to check what happens with the first order equation. And on the right, it's going to be the same. So the first result is that these two notions are the same. Okay? And to prove this, we have to go through an intermediate problem, no? I'm going to illustrate in a very simple case, no? So let me assume that the iconal and Brownian region are separated by a half plane, no? You can also do this with interfaces that are C2 and have, let's say, ball conditions on both sides, no? But just for the sake of the presentation, just consider omega minus is the iconal, omega plus is the Brownian, and they are separated by the plane xn equal to 0, no? And I'm going to call here the restrictions of u to the left and the right, u plus and u minus. Okay? And still we have, well, in the interior of those domains, I have nothing to change, no? I satisfy iconal equation or my Laplace equation. But at the interface, I'm going to ask a transmission condition between the normal derivative, which will be the derivative on the n direction. So here, stop solution means that when I touch you from above, either the length of your gradient is less than 1, or the difference of these two derivatives is negative. Okay? And for stop solution, it will be the opposite. So let me show you geometrically what I'm talking about here. So what I'm talking about here is that sub-solutions tend to look like this, no? They're going to be, they may have a fold at the interface that looks like that. In the distributional sense, the Laplacian may have here a delta measure, no? But it's still possible. Okay? Okay, so let me go to the second part, the more challenging part of this work, which is the comparison principle. So, okay, there are many things that I call comparison principles. So let me be a little bit more clear. So this is called the comparison principle, but there is something else that is called comparison principle in the literature, no? And it says that if you have U, no, a sub-solution of some elliptic equation, and V, a super solution of an elliptic equation, and if they are ordered at the boundary of your domain, then this picture is illegal. They cannot cross in the interior. Okay? This is very good because once you get a comparison principle, you get uniqueness of solutions of elliptic problems. No? So that's what I'm trying to prove here. No? So our theorem, in this case, actually requires that our interface is flat. We don't know how to do this in other type of interface. Well, we know how to do it also if the interface is, let's say, a sphere, but it's very restrictive. No, we cannot do Lipschitz or whatever. It's infinity interfaces. No, so okay, our interface is flat and having the iconal equation to the left, the elliptic equation to the right, and then if they're ordered over the boundary, they are ordered in the interior. No, and omega is a bounded domain. It's a common assumption. So what would be the idea? Let me explain what happens in one dimension, tell you what are the challenges in bigger dimension, and say how we can prove that. So let's assume that U and V, no, are actually a sub-solution and a super solution. However, they cross each other like that. Okay. So what I'm going to do is I'm going to bring it down, and let me assume for the moment that everything is smooth. Okay. There is a challenge with the theory of viscosity solution. It's not obvious, no, that the comparison principle for smooth solutions implies the comparison principle for viscosity solution. It actually took more than 10 years, more than a decade to show that in full rigorosity. But this is just to give you an idea, because this problem has already many challenges, no? So let me say, so I have a sub-solution and a super solution, however, they cross in the interior. So I'm going to bring the sub-solution down until it touches the super solution, no? Here I'm using that omega is bounded, so I have compactness, compactness, and I can just separate them and say something like this. At the contact point, I usually get a contradiction with the monotonicity of the operators, no? At this point, U, remember, for U, you satisfy something like this, and I'm going to assume that this is a strict. And for B, you have something different, no? At that contact point. But however, the comparison principle also tells you that over there, you should have something like this, no? But that's impossible. That's just saying, no, the other way around, no? That's just saying that a negative number is bigger than a positive number. So when what is the challenge in this proof? Well, if the contact point here falls in the Brownian region, in the interior of the Brownian region, you are done. Nothing to do. If it falls in the interior of the Conal region, you are done. There is nothing to do. Now the only challenging case is when the contact point falls at the interface, no? So in this picture, I'm considering that the functions are touching at the interface, okay? So to the left, U is a sub-solution. Yeah, it's a sub-solution of the Conal equation. So its derivative has to be between -1 and 1. Yeah, so you have to be trapped in this region where the slopes are between -1 and 1. And V is a function that is above that, no? And its gradient has to be, its derivative in absolute value has to be bigger than 1. It has two possibilities, no? In fact, it could be over here, or it could be over there, no? If I want the gradient to be larger than 1, I start at this point. But it cannot be below here because I'm assuming that V is touching U from above. Okay? And now let's see what happens to the right. No? I'm saying here that U has to be again between a slope 1 and slope -1. And here what I'm using is a strong equation. So before in this statement, actually I'm using that the Conal equation goes all the way up to the boundary, no? Up to the interface. So once again, U has to be trapped in this other region. Okay? And V, no, has to be again above U. But that is going to imply that this line, no, that has a slope -1 is touching V from below at the origin. But that's a contradiction because V is a super solution of the Conal equation. Its gradient has to be larger than 1. Okay? So it's just a, let's say, technical but easy application of the notions of viscosity solution. What happens now in many dimensions, in several dimensions? Well, like as before, we're going to set up the proof, assuming that U and V are strict sub and super solutions that touch at the origin is at the interface. Okay? And you may even assume that they satisfy the equations in the classical sense on the left and the right. No? So the first thing that we're going to assume is that these functions have some regularity. How do we do that? There is this construction that are called infant subregularization, that or infant subconvolution. No? In general, the type of convolutions that works well with this type of nonlinear problem out of the following form, no? So let's say U epsilon is the supremum, no? Over at X, the supremum over Y of U Y minus 1 over epsilon Y minus X. Yeah? The advantage of this type of thing is that if U is a sub-solution, no, it turns out that U epsilon is also a sub-solution of the problem. They converge locally uniformly to the original function, and moreover, they gain regularity. This function becomes semi-concave. Okay? And in this case, what we're going to do is this type of regularization, but along the directions that are parallel to the interface. So that means that at the point where the functions are touching each other, so U and V, no? This function is semi-concave, and the function is semi-convex. Semi-concave means that at every point you have a paraboloid from above, and semi-convex means that at every point you have a paraboloid from below, but these are n-1 dimensional paraboloids. It's only the dimension of the interface. So at the contact point, you are trapping these two solutions between two paraboloids, and then some elliptic regularity estimates tells you that in fact, if U and V satisfy, if U satisfy an elliptic equation to the right, this is going to be a differentiable function at this point. Clearly, the gradient exists in the tangential direction. The problem is to show that the gradient is also well defined toward the extension, no? And then you have to do something similar for the Connell equation. For the elliptic equation, this is a result of Caffarelli of the 80s, you know? He's famous because he never wrote this theorem, and it's written in some book of differential geometry, and Gilbert and Trujillo also said, this comes from here, and here is the proof, no? Okay, so, more or less, at the point where you already have the regularity estimates for U and V, you can extend the proof that I did in one dimension, okay? So the rest is something very, very similar to what I already illustrated. So to finish, I want to say what are some of the projects, no, that we're doing now. After we conclude this, let's say, well-posedness theory of the problem with just one player, what we want to do is to say that, well, now that we know that this equation has solution, no, for one player, we will expect, let me look it. So here is my one player problem, no? And here is the region omega Brownian and omega Icona. And the first player can always, well, I choose my region and then figure out what is the solution of that problem, of the transmission problem, no? And what is the goal of the first player is to maximize the value function, no? So for every choice of omega b, I have a function u omega b, no? And if I maximize this in omega b, no, we should expect that this gives us the function u that satisfies the problem that we studied with data. Well, we have some ideas, but we still don't know how to get a comparison. We need some to extend the comparison principle that we did over here, no? All the project that we are doing with Arturo, no, is to show that the numerical scheme for this problem converge, no? When you said that you have compactness, no, and recover viscosity solutions of both problems. And the third thing that we started recently with Mariana is to study the regularity of the free boundary, which is quite challenging because this is a free boundary different to the obstacle problem, or let's say the one-phase problem. Usually the free boundary belongs to a level set of a function, no? Usually the function is equal to 0 at the free boundary. But in this case, the function is not 0, no? So There is an additional dimension where you need to control what happens with the singularity of your solution, no? So we're trying some classical methods, but there's still a lot to think about. Thank you very much.